Okay, so my iPad shut off again. Lost my memory. Don't buy a 16 gig iPad, folks, if you plan on making videos. So where was I? I was at 3 equals negative 1/2 times 3 plus b. I knew that my slope was negative 1/2 and that my line passed through the point 3, 3, which is why I put those numbers in there. Put 3 in for x and 3 in for y and negative 1/2 in for m. So let's solve that for b. I'm going to simplify this multiplication over here. That gives me negative 3/2 plus b on the right, 3 on the left. Using the addition property of equality, I'll add 3/2 to both sides. I get 3 plus 3/2 equals b. Now let's go ahead and simplify this addition. How many halves is 3? Well, if I put a 2 in the denominator, I've got to multiply by 2 in top. So I get 6 halves is the same thing as 3, which makes sense to me because 6 halves of a pizza is 3 whole pizzas. So 6 halves plus 3 halves, that's 9 halves. So I get 9 halves for a b. I already found m, so I've got my m and my b, so I'm finished with my equation. It's negative 1/2 x plus 9 halves. All right. So a couple more things I want to talk about are the parallel and perpendicular postulates. That was goal number 3, to discuss those. Okay. Let's look at, you can open up your textbook to page 130. You'll see the parallel and perpendicular postulates both there. Okay, they're postulates in our textbook because our textbook, remember, uses mostly synthetic geometry, which is a word that I've used before. Synthetic geometry is geometry that depends on constructions because individual points don't have coordinates. On the other hand, analytic geometry is geometry that was developed after the Enlightenment by people like Descartes and Fermat. It doesn't depend on constructions, it depends on equations, on solving equations, and the points do have coordinates. Okay, so in synthetic geometry, a line is an infinite set of points that extends in both directions. In analytic geometry, a line is a set of points that satisfies an equation that looks like y equals mx plus b. So we can actually demonstrate the parallel postulate and the perpendicular postulate using synthetic geometry, which is what I'm about to do. So let's look at the parallel postulate. The parallel postulate says that for any line, there exists another line that's perpendicular to that line through a given point. So if I'm given a line and a point, I can always find a parallel line or a line that is parallel to the line that I started with. So that's pretty easy. So suppose we have a line that looks like y equals mx plus b1, let's say. So we've got y equals mx plus b1, and let's identify this point here as the point 0b, which is the y-intercept of the first line. Well, we've already discussed the fact that the y-intercept of a line is where it crosses the y-axis, and parallel lines are lines that don't intersect, and so they just cross the y-axis in different points. And so the other line that's parallel has the same slope and just crosses the y-axis in a different point. So the line, the other line is y equals mx, so it's got the same slope, but it's got a different, it's just got a different y-intercept. We'll call it b2. So here's the length b, oops, I called that b, let's call it b1. Here's the length b2, it's the y-intercept of my second line, and the distance between those two lines, actually let's say the length of the segment on the y-axis between those two lines would just be b2 minus b1, assuming that the parallel line is above the original line. The second postulate is the perpendicular postulate. You can find the perpendicular postulate on the same page, on page 130 of your textbook, and the perpendicular postulate says that, again, for every line and every point, or any point, I should say, not on the line, there exists a line perpendicular to the first that passes through the given point. Okay, so again, we already know how to find this line. Here's my x-axis and my y-axis. In fact, I believe I've already done some examples where we do this. So given the line y equals mx plus b, you can find those examples, by the way, in the Chapter 3 Intro 1 video, I believe. So if you'd like to see those examples, go back there. I talk about the relationship in those videos, that first series of videos, of the relationship between slopes of parallel and perpendicular lines. These lines are perpendicular, so I know that their slopes are negative reciprocals. Excuse me. So the slope of this perpendicular line is negative 1 over m. So I get negative 1 over mx, and then I'm just going to write that it's plus b2. Okay, and how would I find this b2? I would find this b2 by plugging in the coordinates of this point and the slope that I know and solving for that b2. Okay, so the perpendicular postulate is really just a consequence that the synthetic geometers like Euclid didn't have the power of algebra to demonstrate. So they just took it for granted because it was demonstrably true. By demonstrably true, I mean you can demonstrate that it's true by a construction. So really quickly, I'm going to construct a perpendicular line, okay, a line perpendicular to this line. So I've got my line, I've got just some random point out there here, so you don't think that I'm cheating by giving myself a nice easy point. I'll erase this point and do another one somewhere else. There, that one's like off the beaten track a little more. Alright, so what we're going to do to construct the perpendicular to this line that passes through that point, I've got my handy dandy bow compass here, my metal bow compass, so it doesn't break on me. What I'm going to do is I'm first going to make a circle. Let's call this point C and this line L. I'm going to make a circle centered at point C that passes through line L. Just needs to pass through line L in more than 2 places. So as long as the radius of the circle is farther than the distance between the point and the line, that will suffice. However, a longer point, a longer one makes it easier. My point C is kind of close to the end of my line, so I'm a little restricted so that both of my points go through. So there we go. I've got a new point of intersection here and a new point of intersection here which I'm going to draw. Okay, now the perpendicular to this point, or excuse me, the perpendicular to this line is just going to pass through the bisector of this segment. So I'm going to set my compass to the length of the segment to construct the bisector. There's an arc down at the bottom. There's another one. Okay. And I'll grab my handy dandy straight edge. Did I say handy dandy compass and handy dandy straight edge? That's silly. And if I mark a line going from C to the intersection I just made, you can see that that's a pretty darn good perpendicular there. So we'll call that point I for intersection. Okay, so as a summary of the steps for this construction, we construct circle C. So that line L is secant. Secant means intersects the circle in two places. Number 2, we bisect line L. And number 3, the perpendicular, that means the perpendicular line, is line CI. Or maybe if we called this point M. Yeah, let's do that. Since I said bisect L, let's assume that we've given that little segment in midpoint M, and we'll say that the perpendicular is CM. So there's our perpendicular. So this is cool. I really like using algebra and synthetic geometry. It's really good. It's a good exercise for your brain to be able to do this and to also find the equation of this perpendicular. Okay, there's really important relationships between those two things that are really, really complex. Okay, so our final goal, goal number 4 for this series of videos was to describe transversal relationships. So the first thing I need to do is introduce what a transversal is. Okay, we're talking about lines and how they intersect. So you might figure that a transversal is some sort of arrangement of intersecting lines. And you would be right if you guessed that. So what is a transversal? A transversal is made when two lines, such as these two lines, are intersected both by a third line. So this geometric object is called a transversal. It is made up of 3 lines that intersect in 2 places. The third line intersects each of the others, so there's 2 intersections we're interested in. The most interesting transversals are transversals in which these 2 lines are parallel. I've drawn them here so that they don't look perfectly parallel, because if they're not parallel, they're still a transversal. Okay, so I'm going to label the angles that are created by the transversal, 5, 6, 7, 8, in this manner. Okay, and then I want to talk about different types of angle relationships. So, the first is called corresponding angles. Corresponding angles are angles that appear in kind of the same place with respect to their two intersections. So we see we kind of have like 4 angles in a sort of arrangement here and here. The angles that correspond are angles out of the 4 that are kind of in like the same location with respect to like top left, top right, bottom left. So for instance, angle 1 and angle 5 is a pair of corresponding angles. I just wrote a 2, don't know why. So angle 1 and angle 5 are a pair of corresponding angles. Another pair of corresponding angles is, let's say, 2 and 6. So we've got 1 and 5 are corresponding. Also 2 and 6 are corresponding. 4 and 8 are corresponding. And lastly, 3 and 7 are corresponding. The next type of angle relationship is alternate exterior. I'm going to use this symbol, alternate exterior angles. Alternate exterior angles are angles that appear on alternate sides of the transversing line. That's the line that cuts both of these lines. So they're on alternate sides, and they're also on the exterior of the 2 lines that are being cut. So I'm getting some colors. So I'm going to color my interior yellow. So the interior of my lines being transversed is yellow. The exterior of my lines being transversed is green. Okay. So alternate exterior angles are angles that are both in green but on different sides of this transversing line. So let's make one of them darker than the other on this side, and one of them darker on this side. Okay, so maybe we've got like a dark green kind of and a light green. Okay, so alternate interior angles in this diagram are angles that are a pair of dark green and light green, like 7 and 2. And 8 and 1. Those are both examples of alternate exterior angles. The next is alternate interior angles. Okay, those are angles that, you guessed it, are on different sides of the transversing line, but are in the yellow zone. That's the interior of those 2 lines being transversed. Okay, so I've got a dark yellow and a light yellow, 2 pairs of those lines that are on the inside and on different sides of the transversing line. So the alternate interior angles are going to be 3 and 6 and 5 and 4. And then lastly, we have same side interior. Same side interior are also sometimes called consecutive interior. Your textbook refers to them by both names. Right? So same side interior. The same side refers to the transversing line, so they're on the same side of the transversing line, and they're on the interior of the 2 lines being transversed. So they're in the yellow zone, but now on the same side instead of opposite sides. So those pairs would be 4 and 6 and 3 and 5. Okay, so throughout this chapter, the main focus is going to be on transversals. So please familiarize yourself with these angle relationships and with what a transversal is. It's going to be really important moving forward that when I say corresponding angles, you know exactly what I'm talking about. And when I say alternate interior angles, you know exactly what I'm talking about. So thanks for watching. have a wonderful day. Bye.